Good morning, everyone, and welcome to the Murata webinar. Thank you for joining us today. My name is Hans-Peter Lüdecke. I'm the Senior Product Manager for Power at Murata in Europe, based in Germany, and I'm going to be accompanied by my colleague Chris Perkins, also Product Manager for Power, as well as our Principal Design Engineer Frank Vaughan, both based in the UK. The purpose of this series of seminars is to introduce Murata's DC-DC converters that are used in gate drive applications. Often challenges present themselves in many different ways, and we will focus on some of those areas today. The webinar is the first in a series of 3. Today we will look at the basic characteristics required from a DC-DC converter in gate drive applications. The next webinar will look at some application examples with the various pitfalls to look out for, and the third webinar in the series will discuss the way the DC-DCs are qualified for safety and reliability for long service life with some comparative data between other DC-DC types. Let's look at the application now in some detail, and then we'll go through the critical DC-DC parameters, which are its power rating and how to calculate it from the application, the DC-DC output voltages needed for different power switch technologies, the isolation requirements of the converter, its isolation capacitance, and its dV by dt rating or immunity to transients across its barrier. The experts among you, we kindly ask for some fairness towards the less experienced participants. Please allow us to cover some slides about more generic issues first. Let's consider the application. Semiconductor switches such as IGBTs and MOSFETs of all types are used extensively to switch power to a load. The load could be a motor, a welding machine, an AC grid connection, a battery. There are many possibilities. The switch needs to be controlled by pulse width modulated or PWM on-off signals to its gate, and with large devices, significant power is needed to do this because of the high gate charge of these types of power switches. The on and off drive voltages are critical for best efficiency and low EMI, so the gate drive circuit has to be carefully designed and powered correctly. This is where the DC-DC converter comes in. The slide shows a simplified driver circuit for a MOSFET with its gate driven on to +20 volts or off to -5 volts controlled by a PWM signal. The DC-DC converter shown is providing the power for the driver, and it also provides isolation from the supply powering the DC-DC, labeled as VCC to the switched voltage. A complete circuit for sure would have capacitors on the power rails to provide peak currents, and there will usually be protection and fault monitoring circuitry around the gate. Looking in more detail at a high side switch, you can see that the PWM signal is isolated, typically through an optocoupler, and the power rails for the driver are isolated through a DC-DC converter. This allows the 0-volt return on the DC-DC converter output to float and be connected to the source of the MOSFET, which is a switching node. If you connect an oscilloscope from the DC-DC converter input return to output return, you would see a continuous pulsed waveform with an amplitude of the high voltage power rail. This power rail, labeled HVDC, is sometimes not so high. It might only be 24 volts for a low voltage motor, and in this case the DC-DC converter is not normally used. However, the DC-DC becomes the right solution when the power rail is hundreds of volts or higher. Typical values seen are 380 volt DC from a 230 volt AC main, rectified and power factor corrected, or maybe 1000 volts from rectified 690 volts AC, the common industrial power standard. Let's consider now how much power the DC-DC converter needs to supply. The gate of a MOSFET or IGBT looks like a capacitor to the driving voltage. In large IGBT devices, the capacitance can be very high, measured in nanofarads. Each switching cycle, this capacitance is charged and discharged with pulses of current by the driver. Remembering our school physics, we get the result that the power required is the gate charge times the switching frequency times the voltage swing on the gate, or QG times F times Vs. Looking at an example, an IGBT from PowerX type CM150DU with a gate charge specified of 1650 nanocoulombs at 15 volts, switched at 40 kHz, would need 1 watt from the DC-DC converter. With an actual gate voltage swing of 25 volts, 20 plus 20 volts for turn on, and minus 5 volts for turn off, power need will be 1.65 volts. The gate charge value is found from the device datasheet, listed as QG or total gate charge at a particular gate voltage. It is not a very exact figure, so some margin should be allowed. Also, the datasheet will often state the gate charge at a different voltage swing to what you want. You can simply proportion the charge to the voltage swing you want. For example, the PowerX part datasheet gives a gate charge of 1650 nanocoulombs at 15 volts swing. At 25 volts swing, the charge is simply increased by the factor of 25 divided by 15, giving 2750 nanocoulombs. It's not unusual to calculate that several watts of power are needed. So, where is this power dissipated? It is dissipated in the internal gate resistance in the device and in any extra external resistance that is introduced, and some is for sure dissipated in the driver transistors. MOSFETs generally have lower gate charge than IGBTs, so the calculated power can be much lower. However, MOSFETs can run at much higher frequencies than IGBTs, so we do see MOSFET applications at high frequencies where many watts are still needed because of our equation. Power needed is proportional to switching frequency. For example, the large silicon carbide device from Rome is the BSM300 series. It has a gate charge of 2 microcoulombs at 25 volts. If you switch this device at 400 kHz, you would need 20 watts of gate drive power. Don't forget that the DC-DC may also be providing power for fault detection and signaling, so this will add to its load. Here are some examples of the power needed for driving the gates to a selection of devices. We have an IGBT at 10 kHz with a very high gate charge requiring 1.74 watts, a silicon MOSFET at 100 kHz requiring 0.34 watts, a silicon carbide MOSFET at 100 kHz requiring 0.5 watts, and a gallium nitride device at 1 MHz requiring just milliwatts. The gate voltage swing in each case is different and is typical of what might be used in a real application. Murata has a freely available database of IGBT and MOSFET part numbers with gate drive power calculated for a range of switching frequencies, along with recommended DC-DC converters in a selection of form factors, including through-hole and surface mount. We also have an Excel-based calculator which allows you to put in the device parameters and actual frequency separately to give gate drive power along with peak and average current required from the DC-DC. We've sized the DC-DC for power, but what about voltage and current? If you look at IGBT or MOSFET data sheets, you can see that there is quite a wide tolerance on the gate threshold voltage for switching, and the margin and the margin between this value and the absolute maximum. However, a system designer will choose the voltages that give the very best efficiency from the device and the best EMC performance. We have also seen already that a high voltage swing gives higher gate drive power, so the voltages are chosen carefully. For IGBTs, they might be plus 15 volt and minus 9 volts. A silicon MOSFET could be plus 20 volts and minus 5 volts, and the latest silicon carbide type might be plus 18 volts and minus 3 volts. It's important that these voltages are kept within about 10% and that they are accurate at the calculated load. In fact, the load on the DC-DC is constant and does not depend on the PWM duty cycle because the gate capacitance is charged and discharged every cycle, whatever the duty cycle. So the total energy and average current is the same. Another condition is when the power switch circuit is not operating or is perhaps shut down in a load fault condition. In this case, the load on the DC-DC converter drops to near zero. This means that a DC-DC converter whose zero load voltages go very high is not suitable. When the load starts operating, these high voltages could cause stress to the gate until they drop to their correct operating value. The MGJ series of converter all have clamped output voltages so that at no load they are limited to safe values. Another consequence of the power switch gate charging and discharging is that the average positive and negative current needed to drive the gate voltage, positive and negative, is the same. It only depends on the total voltage swing. This means you will see DC-DC converters for gate drive applications with, for example, output voltages of plus 20 and minus 5 volts at the same current rating. The current required to drive the gate capacitance is taken as a spike at the edge of the switching waveform. The amplitude of this current spike is only limited by the internal and external gate resistance and can be quite high, typically several amps. If the DC-DC converter were to be rated to give this continuously, it would be very large. So external capacitors on the power rails are used to supply the peak currents, while the DC-DC have a much lower average current rating to recharge the capacitors over each switching cycle. The capacitors have to be chosen carefully to have the right rating for ESR as well as capacitance to avoid stress. If they are too low in value, some of the peak current is sourced by the DC-DC converter, which could cause excessive ripple and overheating. We are often asked why the gate drive voltage needs to go negative because a typical IGBT or MOSFET used in power switching will be off with 0 volts on the gate. There are several reasons based on the fact that the turn-on threshold can get close to 0 with temperature and time, and it can also change, going lower. Silicon carbide devices, for example, can have threshold voltages of around just 1.5 volts at high temperatures. A negative voltage allows the turn-off point to be better defined, and it helps to overcome voltage transients caused by lead inductances and the Miller effect, which try to turn the device spuriously on. We look at each of these effects next. Remember that the power device gate is like quite a large capacitor CG, and there will normally be some external gate resistance RG in the circuit, so even if the drive waveform has a very short fall time, the RC discharge effect of the resistance and capacitance slows it down with the gate connection at the semiconductor die. Sometimes this is designed to be slow to help with EMI. That if the off voltage is driven to 0, as shown in the left side plot, the voltage goes through the threshold point relatively slowly, and if the threshold can vary with tolerance, the switching point varies as well. If the target off voltage of the gate is negative, as shown on the right-hand plot, the threshold is passed more quickly with less variation in the switching point with time and less risk of excessive power dissipation during the switching edge. Another effect to consider is the stray inductance around the power switch and even inside the switch package. When the gate is driven off, the load current falls at a fast rate to give low switching losses. This rate can easily be 200 amps per microsecond or more. Changing current through an inductor produces a voltage drop from the familiar equation E equals minus L times dE by dt. So even a low value of inductance will produce a voltage transient. If the inductance is between the device and the reference point for the driver, as shown in the slide, the voltage transient acts to oppose the gate off voltage and tries to turn the power device on again. At best, this can cause loss of efficiency and at worst, shoot through, which can cause extensive damage and system failure. To put a scale on it, you only need 10 nanohenries of inductance to produce a transient of 2 volts with 200 amps per microsecond. This is only about 10 millimeters of tracking. Remember from our last slide that a silicon carbide MOSFET can have a switching threshold voltage of just 1.5 volts. Driving the gate to at least 2 volts negative offsets the transient voltage during the transient voltage producing more reliable operation. As an example, the package-induced inductance of a typical IGBT from Vishay, type VS-GB75, is a maximum of 30 nanohenries, which would produce a 6-volt transient under the same conditions. However, devices like this usually have a Kelvin connection, where the driver reference can be connected. This should always be used if available. Smaller devices are sometimes in the 3-pin TO247 package, where the inductance of the source or emitter connection is unavoidable. Kelvin connections at emitter of a device like an IGBT do not help stop the effect of Miller capacitance producing transients. What happens is that when a power device turns off, its collector goes positive. This produces a pulse of current through the device internal capacitance Cm, marked here with a red circle, from collector to gate. This is the so-called Miller capacitance. The pulse of current flows in the direction of the arrows in the diagram through the gate emitter capacitance, as also back into the driver circuit. Both current passes produce positive voltage drops which tend to turn the IGBT on again. Driving the gate negative again helps to overcome the effect. Another major parameter for a DC-DC converter in a gate drive application is its isolation rating. We know that in a high-side application, the DC-DC has a continuous high voltage across its isolation barrier. Most general-purpose DC-DC converters that claim 1 kilovolt or 3 kilovolt or even 5 kilovolt isolation are totally unsuitable, as this voltage is a test rating applied for 1 minute only. These parts will fail quickly unless they are specially designed for the high continuous voltage. In a later webinar, we will look at some examples of stress testing to show the differences between general-purpose DC-DCs and the gate drive versions. Even if the DC-DC has isolation rated for high continuous voltages, if the DC-DC is part of a safety isolation system in the end equipment, it will need a level of safety certification. This may limit the voltage stress allowed. For example, the Murata MGJ2 series is tested in production at 5.2 kV and has been shown to work reliably with 3 kV continuously across its barrier. However, if it is part of a safety isolation system needing reinforced rating, the high voltage DC allowed is just 210 volts. This is because of the safety agency evaluation of the internal construction of the converter. If higher levels of reinforced safety isolation is needed, you can choose other parts in the Murata range. For example, there is a 6-watt converter which is rated for a reinforced isolation right up to 1000 volt in 690 volt AC systems, which includes creepage and clearance distances of 14 millimeter. Not all applications need full reinforced insulation in the DC-DC converter. For example, if the connections on the input side of the DC-DC are fully enclosed and cannot be touched, then the lowest safety agency level, functional, is adequate. Sometimes there are several isolation barriers in series providing the equivalent of the reinforced rating. In this case, the DC-DC may only need an intermediate rating of isolation, perhaps basic rating. But this all depends on the power system architecture and needs to be looked at case by case. Looking now at coupling capacitance, we know that in a high-side application there is continuous high-frequency waveform across the DC-DC converter, so this will cause current to flow through any coupling capacitance between the output and input of the converter. You might work out the impedance of the coupling capacitance at your PWM switching frequency, and with the switched voltage, expect a current of only a few milliamps to flow. However, the sharp edges of the waveform cause transient current to flow, given by the equation I equals C times dV by dt, and dV by dt can be anything from 10 kilovolt per microsecond with IGBTs to 100 kilovolt per microsecond and higher with wide bandgap devices such as silicon carbide MOSFETs. If the capacitance is, say, 10 picofarads and the dV by dt is just 30 kilovolt per microsecond, then the current spike is 300 milliamp. This current finds a return path to the switch through the system earthing and will cause voltage drops across resistances and inductances. The voltages add to EMI and can cause interference or even malfunction of the control electronics. It's therefore necessary to choose a DC-DC converter with as low a capacitance as possible. Values down to 3 or 4 picofarads are achieved with some of the converters in the Murata MGJ range. If the level of current is still too high, you could fit a common mode choke in the input of the DC-DC converter to reduce it. In a related effect, The high switched voltage across the DC-DC converter also causes stress to its insulation. The edge speed of the waveform, so the dV by dt, causes stress as well as a voltage amplitude. This can cause long-term damage and failure. In a later webinar, we will look at the different types of insulation and how well they stand up to the stress as measured by the so-called partial discharge effects, which is the slow degradation of insulation over long periods when subject to high voltages. We will show that traditional insulation, which may even be good for safety agency ratings, is not necessarily good for partial discharge performance. So, till now, we have talked about how isolated DC-DC converters can be used for gate drive power, but to be fair, there are other ways to generate the power needed. They do have their limitations, though. A very simple way to generate high side voltage rails is the so-called Bootstrap or charge pump circuit. Although it is simple and cheap, the problems are that only limited power is available from the stored charge on C1, and the voltage on C1 depends on the main switch duty cycle. It only generates a positive rail, so the gate cannot be driven negative unless further circuitry is added. The components must also be chosen very carefully. For example, D1 has to be a high voltage diode with very low reverse recovery, and R1 is needed to limit P current into C1, which then reduces the accuracy of the voltage even further. D1 is also a critical component for reliability. If it fails, the driver for Q2 will be destroyed, possibly along with many other components. Perhaps the biggest problem with this technique is that the high side gate drive power is only there when the power devices are switching. So on startup and during fault conditions, like a load short circuit, the gate is not well controlled and there is no power available for high side fault protection and monitoring. Generally, if the efficiency and fault tolerance of the system is important, the gate drive voltage is critical, and a bootstrap circuit is a poor compromise. A final limitation is that there is no safety isolation between high voltage rail and the low voltage VCC used to generate the high side gate power. Of course, VCC can be generated with a high isolation DC-DC converter, but that defeats the simplicity of a charge pump. You might as well use the DC-DC to provide the high side voltage rails and get all the benefits of continuous power and well-controlled voltages. Another way to drive gates is directly through a transformer. This provides isolation and is relatively simple, but the transformer will be a compromise because it may need high isolation and watts of power, but at the same time it is transferring the PWM signals at high frequency like a signal transformer. Practically, it cannot be optimum at doing all these things together, so it will be limited to relatively low PWM frequencies, which makes it physically quite large. High isolation and large size leads to high leakage inductance, which in turn slow down the edge speed of the PWM waveform, risking power loss in the switches. Of course, the PWM source also effectively has to be a power driver supplying the watts of power needed. You cannot just use outputs of logic gates, adding again to cost and complexity. All transformers like this have to have a zero net magnetization after each switching cycle, otherwise they would quickly saturate. This means that the transformer has to be allowed to reset with the same volt seconds on positive and negative waveforms. The reset voltage therefore varies with duty cycle, and to control it adds complication. If the transformer is AC coupled, as in the diagram with C3, it will naturally reset, but now the capacitor will resonate with the transformer inductance, producing low-frequency modulation of the PWM signal until the resonance settles. This will happen on start-up and every time the duty cycle is changed, risking inaccurate gate drive voltages while it happens. Again, when there is no PWM signal, there is no gate drive voltage, so no power for fault detection and monitoring. If the load is shorted, other protection circuitry may operate, reducing the duty cycle to near zero, but then there is little power available from the gate drive PWM signal, and the voltages may therefore drop out of specification, leading to overdissipation or failure in the power switches. Positive and negative gate voltages can be generated, but with extra circuit complexity. Finally, perhaps the major alternative to a modular DC-DC converter is an equivalent discrete design. For very high volume applications, this may always be the lowest cost, but there will be a volume where a module makes sense. The total cost should be evaluated, which includes real but difficult to evaluate benefits, such as savings in size, production costs, overheads in production, test and purchasing, approvals, and as well as design and opportunity costs. Opportunity cost, that is the cost of a lost business waiting for a discrete design to be developed. Some users like the security of knowing a discrete design can be assembled from multiple vendors of components, but the transformer design will inevitably be non-standard and often have to be outsourced. A module can be a quick, high-performance and secure solution. Even cost may be favorable when all overheads are taken into account. Murata Power even has a range of multi-channel gate drive DC-DC converters that can power up to 3 high-side and 3 low-side switches simultaneously, potentially saving the cost of multiple converters. So, thank you for listening to this webinar, and I hope it has been useful and interesting to you. We will be conducting 2 more, with the next one focusing on real-life applications for gate drive power with pitfalls to look out for, and the 3rd webinar discussing the qualification of these converters for reliability and long life. We will be announcing the dates soon.